Welcome back. In this video, we're going to talk about an introduction to Lagrange multipliers. So if you'll recall, in the last problem we did from the last section, we did a problem where we optimized the volume of a box, and we did not use Lagrange multipliers because we don't know anything about them yet. And we're not going to necessarily do them on this either, but we're going to talk about what they would do and how we would use them and how they can simplify our problems. So what these Lagrange multipliers do essentially is, again, they're going to help us find values of constrained functions. So constrained means we have a rule or a constraint that needs to be followed. So for example, in this problem we're going to do, we want to find a point somewhere that is on the plane. So that's our constraint. It's just not any point closest to the origin, but a point that's on the given plane. So that last problem, the domain was restricted by the constraints of the box. The box had to be a certain size. This problem we're going to solve similarly to that volume of the box problem, where we can eliminate a variable. So we'll talk about, we don't always have to use these Lagrange multipliers, but we're going to just look at solving this optimization problem. So here is the plane, 2x plus y minus z minus 5 equals 0. And we want to find a point, P, somewhere on this plane that is closest to the origin. Well, the origin is a point, 0, 0, 0. So being redundant, let's just really think about what is this asking? What we need to do is we have to find the minimum distance from 0, 0, 0 to pxyz, right? And we are subject to a constraint. What is that constraint? That this point has to lie in this given plane. So we're being asked to minimize a distance, which means we need to calculate that distance from the origin to the point P in the plane. So we can calculate the magnitude of OP. And that will just be x minus 0 squared plus y minus 0 squared plus z minus 0 squared, which simplifies to the square root of x squared plus y squared plus z squared. So that is our distance. So we need to minimize this function, and to make our lives a little bit easier, we're going to just disregard this square root, because if I can minimize x squared plus y squared plus z squared, I would be minimizing the smaller function with the square root, which is underneath that set. So our function x, y, z, we're going to call that x squared plus y squared plus z squared. So the distance from the origin to the point P is minimized at the same point or points where the function is minimized. Now, we can't forget about the fact that we have this constraint. P has to lie in this plane. So what I'm going to do here is I'm going to rewrite my function for the plane. I'm going to isolate z. I'll say z equals 2x plus y minus 5. This is my constraint. Now, it's easy to see that a minimum value for this function would occur at the ordered pair 0, 0, 0. But 0, 0, 0, if I plug that into my constraint, that doesn't lie in my plane. So let's use this constraint and plug it in for z to rewrite our f function. So we've got f of x, y, z is x squared plus y squared plus 2x plus y minus 5 squared. At this point, we're happier because we have now reduced this to a function of two variables. And from what we've learned in the previous section, we're going to be able to find that minimum at the critical points, and the critical points come from setting those partials with respect to x and respect to y, this function f, equal to 0. So what we need to do is we need to find f partial x, set it equal to 0, f partial y equal to 0. That's going to create a system that we need to solve. So what does this give us? If we take the partial with respect to x, we get 2x. This goes away. We pull the 2 down. The derivative of the inside is just going to be 2, so I'm going to have a 4. So I have 2x plus 4 times 2x plus y to the negative 5 equals 0. Again, differentiating with respect to y, we'll have 2y plus, we pull that 2 down, and then the partial derivative of the inside with respect to y is going to be 1, so this coefficient will not be 2 times 2, it's 2 times 1, or just 2. 2x plus y minus 5 is equal to 0. So this top one represents my partial with respect to x equal to 0. The bottom is my partial with respect to y equal to 0. Simplifying, just distributing and combining like terms, moving the constants to the right, I end up with a system of linear equations. 10x plus 4y equals 20, and 4x plus 6y equals 10. Now this is a very simple system of linear equations for us to solve. And the solutions, x equals 5/3 and y equals 5/6. So that's my critical point. 5/3, 5/6. So at this xy value, and we can calculate z by going back up and plugging xy into z. But that's where we suspect the minimum value is going to occur. Now, in order for us to prove that it's a minimum, we use the second derivative test for extreme values. Now, looking at what we have here, this top line that I'm pointing at, 10x plus 4y equals 20, that's my partial with respect to x. 4x plus 6y equals 10 is my partial with respect to y. So let me rewrite that. I've got f sub x equals 10x plus 4y minus 20. F sub y is 4x plus 6y minus 10. So my second derivative test, I need those 3 second partial derivatives. With respect to x twice, I get 10. With respect to y twice, I get 6. And in both situations, if I take x with respect to y, I get 4. If I take y with respect to x, I get 4. So I've got my partials. Now I need my discriminant. So the discriminant is fxx, fyy minus fxy squared. Or 10 times 6 minus 4 squared, 60 minus 16 gives us 44, which is greater than 0. So recall, if d is greater than 0, then we know we're going to have a max or a min. And if fxx, in this case it is 10, which is greater than 0, so that implies that it's only a minimum. So the function is minimized when I have this x and y value. Of course, we need z. Recall what z was equal to. Z was 2x plus y minus 5. So my ordered triple here, 5/3, 5/6, and negative 5/6. That negative 5/6 is found by plugging this ordered pair into my z equation previously. So this is my point P, 5/3, 5/6, negative 5/6. It's a fun word to say, sixths. That is the point on the plane which is closest to the origin. And the distance is 5/√6, or approximately 2.04 units between that plane and the origin. So that's the shortest path. All right, so in the next video, we're going to talk about these Lagrange multipliers and show how they can simplify these calculations a bit.